So the University of Washington acknowledges the Coast Salish peoples of this land, the land which touches the shared waters of all bands and tribes in the Suquamish, Tulalip, and Knuckleshoot nations. And our lab also acknowledges that we live and work on the ancestral lands of the Duwamish people, the first people of Seattle. So today's presenter is Lilly McGill, and Lilly asked for a short introduction. Lilly is a graduate student in the Quantitative Ecology and Resource Management program. She is co-advised by Drs. Ashley Steele and Gordon Holtgreave, where she primarily studies freshwater with the ultimate goal of her research being to help resource managers maintain ecosystem function and habitat by understanding what climate-driven changes to rivers have occurred and by developing inexpensive, broadly applicable tools to understand what river basins may be at risk in the future. She graduated from Notre Dame with an environmental science and applied math and stats double major. Lilly is going to try to take questions as we go. I haven't personally given this a shot, but we're going to give it a shot today. So I will try to pass you questions as we go, and then any additional questions she'll take at the end. So thanks everyone for coming, and a big thank you to Lilly for sharing your work with us today. And with that, it's my pleasure to turn it over to you.
Awesome, thanks Abby. So my work today is titled Assessing Hydrologic Change and Spatial Covariance Among Time Series of River Discharge Across Western North America. And this project is ongoing, and so as part of the presentation, I guess if at any point you have questions, comments, insights, potential extensions, I guess I'm happy to take those questions as they come, and I'll try to keep an eye on the questions box in the chat as it goes along. But if I'm not immediately responding, feel free to interrupt and just notify me that there's something there. Awesome. Okay, so with that, I guess I'll start. And to start off with a super broad backdrop, the West Coast of North America has an interesting climate due to the fact that it experiences moisture-rich westerly winds coming in off of the Pacific that then ram into these massive mountain ranges that are shown in brown on the map. And the resulting combination of these weather patterns and topography is that you have a strong gradient of temperature and precipitation over relatively short areas due to elevation gradients. There's also a gradient of precipitation and obviously temperature as you move south to north. And so what this all culminates as is there's a lot of complexity over a relatively short space. This complexity is compounded by adding on the element of climate change. So like much of the world, the West Coast is expected to see increases in temperature, changes to precipitation, and a resulting decrease in the proportion of snow versus rain in winter precipitation. So in terms of changes to precipitation, climate projections are way less consistent than something like temperature, but we do expect to see severity of winter storms increase and seasonal precipitation patterns sharpen, resulting in more intense precipitation over a shorter period of time and a relatively drier summer. Whoops. And so these climate-induced changes will inevitably bring about changes to the hydrology of Western rivers. And so an important thing to note is that the hydrology of these river basins is particularly sensitive due to their dependence on mountain snowpack from the Cascades, Sierra Nevadas, and Coast Ranges. Many Western rivers rely on cool season precipitation that falls in October through March, and the resulting snowpack to sustain warm season stream flows in April through September. And so as climate change will affect the balance of precipitation falling as rain and snow, in addition to shortening the length of time that precipitation falls over, we expect corresponding changes to the timing, duration, and magnitude of stream flow. So all of that was talking about how on a broad scale, we expect to see these changes in hydrology. However, rivers obviously have a ton of heterogeneity across space, and figuring out exactly what changes are predicted requires a bit more of a mechanistic approach. So we expect rivers to respond differently to the same overarching climate signal, depending on what their baseline hydrology looks like. And so an sort of common way to aggregate rivers into groups is by seasonal patterns and discharge. And so the hydrographs, which is just discharge through time, on this slide show the patterns for the three most common types of West Coast rivers. The far left graph shows a rain dominant system where within the basin, most of the winter precipitation falls as rain and discharge is correspondingly highest during the winter months. The far right graph shows a snow dominant system And here, most of the winter precipitation falls as snow, and discharge is highest during the spring and summer as snowmelt occurs. And in the middle, you have a mixed basin, which is just a middle ground between the two rain and snow systems. And so as climate change progresses and increased winter warming results in those changes to the timing and form of precipitation, what process-based models predict is that snow-dominant rivers will become more similar to mixed, and mixed will become more similar to rain. And we care about these projected changes because seasonal flow regimes support river processes such as disturbance regimes, habitat provisions, and native species life history cues. And so what this figure shows is just a schematic representation of an annual hydrograph, I think for California, with associated key physical processes as yellow bars and species needs supported by various flows as the green arrows. And so what should be obvious is that over the course of an entire water year, there are important cues that happen from these environmental flows that species and humans in some way are adapted to. So changing them will have big consequences. So in our highly seasonal, oftentimes described as Mediterranean climate that dominates a lot of the West Coast, you can break up a hydrograph into 4 sections or sort of important components that are shown on this figure here. So the first is just the fall pulse flow, which is just the big first storm after the dry summer. The second is the wet season, and this is when most precipitation occurs. The spring recession defines the transition between wet and dry season, and it's commonly associated with snowmelt. And then finally, base flow is just the hot, dry part of the year when flows are typically lowest. And so for this talk, I'm only going to focus on the extreme high and low parts of the year. So those peak flows and low flows. So starting with peak magnitude flows, we care about them because overbank floods are a well-recognized functional flow component that supports a broad suite of physical and ecological processes, including the maintenance of habitat heterogeneity in space and time, providing cues for fish migration and reproduction, and then controlling patterns of riparian succession. Floods can obviously also have big consequences for humans if high flows cause flooding, which damages property. And then, so the second period of time I'm focusing on is the dry season base flow. This is just the low magnitude, low variability portion of the water year, which occurs in summer. Base flow period coincides with peak demand in the agricultural growing season, and drought years can sometimes pose severe risks and economic consequences for farmers because of decreased crop yields. Low river flows and associated warm stream temperatures also have a range of ecological consequences for native fish, such as Pacific salmon, including things like range contractions, accelerated emergence of fly, and accelerated emergence of fry, and associated phenological mismatch with available food resources like flies. And so each of these periods obviously has important ecological and human components to it. And so for each of these periods, I calculated 2 metrics that capture elements of the duration and magnitude of these hydrologically important events. So specifically, we define the peak flow magnitude, which is just the maximum magnitude of flow in a water year, and the peak flow duration, which is the number of days over the 20th percentile of flow for the entire time series. We do a parallel process for minimum flows, where we calculate the minimum flow magnitude, which is just the minimum flow in a water year, and minimum flow duration, so number of days below the 20th percentile of flow over the entire time series. And so each of these 4 metrics are just annual metrics for a river. All right, so there's been about 1 million studies looking at Western river hydrology, but there are still, I think, a few gaps in the knowledge that exist, and hopefully the study will help to sort of fill. So a lot of studies, when they look at these trends in discharge metrics through time, look at monotonic trends, and relatively few look beyond whether sites have shared patterns in just like the amount of change through time. So whether things are just consistently increasing or decreasing, and by how much. We also expect that the importance of controls varies across both space and metric type. And I think important questions remain as to what the sensitivity of hydraulic extremes are to alternative pathways. So For example, things like global circulation metrics, warming effects on snow, precipitation amount effects, or local effects mediated through things like river type or subsurface drainage processes. Additionally, a lot of studies seem to look at metrics individually rather than in tandem. So I think there are questions that remain as to how trends in hydrology metrics co-vary across space as well. And so the project goals for this are to map the magnitude and extent of changes to those 4 streamflow metrics that I went over, and to resolve the relative influence of local scale morphological and global or regional climatic processes in governing these patterns of change. And so the first step in doing this was simply to classify rivers according to those 3 categories that I mentioned at the start. So rain, mixed, and snow basins. And before I do that, I guess I'll describe the data that was used in this study. So the data used in the analysis comes from a network of climate reference rivers, both in the United States and Canada. And what this means is that these rivers are relatively free of human influences like withdrawals or dams over the years that we're analyzing. The river basins are shown in gray on this map here. So you can see from the network, we collected discharge data from 179 of the rivers, and they span British Columbia, Washington, Oregon, California, and just like a tiny little part of Alaska. The data typically begins between 1900 and 1950, with a trend where there's a later start date for higher latitudes. Yeah, as I said, the watersheds are shown on this map. They cover a wide range of areas. And there's also a pattern, which you probably noticed, where river basins at higher latitudes tend to be larger than ones as you move further south. And that's largely a function of the fact that there's just not a lot of unregulated rivers, large rivers, in California. So from this daily discharge data, we calculated those 4 annual discharge metrics I talked about earlier for each of these basins across all of the years available. So once we had our watersheds, we next wanted to develop a classification scheme for rivers that would allow us to classify them as either that rain, mixed, or snow driven. And so there's a ton of classification schemes out there. Some cluster rivers based on empirical hydrology or watershed characteristics. But we chose to use a more first principles approach that has been widely used in the literature. And it's to use the ratio of maximum snow water equivalent, so how much snow accumulates in a basin, to cumulative wet season precipitation. And this essentially gives us the ratio of snow to rain in the winter when the majority of precipitation falls for these basins. And the ratio was then averaged across all years where I could find data that spanned our sort of study basin or study area. And so from this continuous ratio, we then delineated discrete hydrology classes and classified rivers into either rain, mixed, or snow hydrology. And so what we saw with this, and what you can see on the figure on this slide, was that the ratio between snow water equivalent and winter precipitation, which is the value on the y-axis, and it's logged, I guess I should note maybe, varied strongly with both elevation, which is on the x-axis, and latitude, which can be roughly defined through the colors of points that represent the state where the river basin is located in. And so that for the same snow water equivalent to winter precipitation ratio, you get it at lower elevations in higher latitudes. And the dotted lines on that graph just show the boundaries for each of those classes. And this is totally what we had expected. So it's good to see that it worked. One thing to keep in mind when looking at these classes is that the classifications are really just nodes along this complex continuum of streamflow response to mixed drivers. So the figure on this plot just shows an average hydrograph across all years for each of our study basins. And it's just designed to illustrate general patterns in annual streamflow, where the x-axis of this is the day of the year, and the y-axis is standardized discharge across all years that we have data for. And the color is just defined by whatever state a river is in. And so what should be apparent by this is that there's a big diversity of patterns within any given hydrologic class, particularly for those mixed hydrology basins, which display super diverging patterns in what they look like. And so one additional note maybe is that using this SWE to winter precipitation ratio captures climate influences, but ignores processes like groundwater or subsurface processes, which is something potentially we will add in future iterations of this project. And so all this just culminates to say that the classification is useful, but very general. And the last bit I want to point out for this is just the spatial arrangement of these hydrology types. So snow watersheds are mostly located in British Columbia, and rain watersheds are predominantly found along the Pacific coast and into California. And I guess I will say also that these color schemes where red is rain, purple is mixed, and blue is snow are going to be used throughout the presentation. So just maybe keep that in mind. Makes it easier to understand the graphs. Okay, so that leads me to sort of the first question of this project, which is just, are these streamflow metrics changing monotonically through time? And I wanted to add this part in partly to have a basis of comparison with the next trend analysis that I do, but also to have a basis of comparison with previous studies, because this is what I guess most of the studies that look at these trends through time have used. And so to do this, to see if trends are changing monotonically, I used, I think, like the most common trend analysis tool, which is the Mann-Kendall trend test. The Mann-Kendall test, it's a rank-based approach, and it's non-parametric, and it's been really widely used for detecting trends in hydrology time series. So for a given time series, the null hypothesis of this assumes that it's independently distributed, and the alternative hypothesis is that a monotonic trend exists. And so the Mann-Kendall test analyzes the differences in signs between earlier and later data points. And the idea is that if a trend is present, the sign value will tend to increase consistently or decrease consistently. And so every value is compared to every value preceding it in the time series. And so that gets you whether or not a trend is significant. And then in order to compute trend magnitude, what people usually do is use the Thiel-Sen slope estimator. They basically equivalent to just a linear regression slope if the data is normally distributed, but it's robust if you have outliers. And it basically is just computed as the median slope of all data pairs. Yeah, so what these graphs show are results from the Mann-Kendall trend test for our minimum flow metrics. And so the x-axis is the Kendall-Tau slope estimate, which is just that estimate of how steeply the metric has increased or decreased through time. The gray dots are basins that were not significant according to our criteria, which was just a cutoff of the p-value. And then basins that are colored were significant, and that color is just defining the hydraulic class. And it should be noted maybe that all data I talk about from here on out was centered and standardized prior to analysis. So what we see for this is that minimum flow magnitude for those time series trends are generally decreasing, except in some high latitude areas where they're increasing, likely due to the melt of permanent snow or glaciers due to higher temperatures. And there isn't really much of a response in the trend in terms of rain or mixed basins. The biggest difference comes with those snowmelt basins. And so for minimum flow duration, we see nearly all basins beginning to have longer periods of low flow, but fewer significant trends overall. So Mann-Kendall results for maximum flow metrics overall show far fewer significant trends and overall less consistent trends. For peak magnitude, we have 30 significant trends with 21 of them decreasing. All of the ones that are increasing tend to be located in the Pacific Northwest. And for peak flow duration, we have even fewer significant trends and less consistent patterns, with 12 significant trends, 10 of which are decreasing. And these results, both for the minimum flow metrics and for the peak flow metrics, are on par with what another study found, looking at only in the Pacific Northwest, where there's generally a lack of consistent and significant trends in flood magnitude. And so the last thing that I want to talk about with the Mann-Kendall monotonic trend results is just looking at how maximum and minimum flow metrics co-vary. So what these figures show is that the duration slope estimates for all basins, not just the significant ones, are on the y-axis. So you have minimum flow duration on the left and then peak flow duration on the right. And on the x-axis, you have those magnitude trend estimates. So again, minimum flow versus magnitude. Minimum flow versus peak flow. And what we see is that for minimum flow metrics, rain and mixed watersheds show more correlated changes through time than snow watersheds. So basically, if you have a lower minimum flow, you're more than likely going to have a longer period of low flow, as long as it's not a snow watershed. And then for peak flow metrics, sites overall show a less correlated response, where just because you have a higher peak flow doesn't necessarily mean you have more days of high flow. And so takeaways from this are just that monotonic trends are stronger for minimum flow metrics than peak flow metrics, although overall, the majority of basins don't show any significant trend. Snow rivers tend to have different rates and patterns of change compared to rain and mixed watersheds, and then minimum flow metrics co-vary more strongly than maximum flow metrics. Okay. All right, so now that was just looking again at monotonic trends. But as part of this analysis, we wanted to move beyond looking at these just up or down trends and ask, do we see common trends in river discharge time series? And are the common trends caused by basic specific characteristics, or are they more indicative of regional or global climate signals? And so in order to do this, we use dynamic factor analysis. This is a flexible time series approach. And DFA is a dimension reduction technique which models n observed time series. In this case, 179 time series from each of our rivers of those four sort of hydrologic metrics. As a function of m hidden states, where the number of time series is much greater than the number of hidden trends through time. And so what this means visually is that if you have a whole bunch of time series that sort of appear to be doing their own thing, what DFA will do is look for common patterns in those time series that explain the greatest amount of variation across the greatest number of time series. And so the number of sort of hidden states or latent trends is selected by the user, but it's common practice to test multiple m's or multiple numbers of hidden states and see what data support is the greatest for each of the numbers. And so the equations that define the DFA model are shown here. Equation 1 is the state equation that defines the shared trends through time. I'm also going to call them the latent trends, I guess, so that might be interchangeable. These trends are estimated by the model and follow a random walk through time so that they're fairly flexible in terms of what shape they can take. And again, we specify the number of trends to fit, but not the format of those trends. So the trends can take any shape that maximizes variance explained in the data. Equation 2 is our observation equation, where the response variable is our discharge metrics for each site. So YT is going to be a 179 by 1 vector of a given discharge metric at time t. And the model specifies that our YT, or our observed data, are a linear combination of latent trends, covariates, and some error that's distributed according to a multivariate normal distribution with that variance covariance matrix R and zero mean. And so the Z matrix is a matrix that's going to be size 179 by whatever number of latent trends we choose, and it contains the loadings onto each latent trend. The Z matrix determines basically the linear combinations of common trends for a given site. So factor loadings can be thought of as sort of effect sizes or coefficients, and they're often compared to one another to determine which response variables are most strongly related to each common trend. Explanatory variables are added through this d times dt term, where d is just our matrix of coefficients for each of the covariates, and dt is a vector of our covariates at time t. So in these models, we tested a combination of multi-scale covariates, including global and regional drivers. So for global drivers, we included both summer and winter values of the El Nino Southern Oscillation and Pacific Decadal Oscillation indices. Both PDO and ENSO indices characterize variability in sea surface temperatures over the Pacific and influence weather patterns across Western North America. So people have probably heard that this winter is a La Nina winter in Seattle. And then a primary difference between the two is that PDO captures decadal scale variability, whereas ENSO events tend to persist on the order of a year. Additionally, although both processes influence the entire Pacific, ENSO primarily affects the climate of lower latitudes and PDO primarily affects the North Pacific region. For regional drivers, we have mean annual and maximum and minimum monthly temperature and precipitation. So since we needed covariates that spanned our entire time series, which for some rivers goes back to 1900, spatially distributed models that give historical values tended to start much later than we needed. So although it would have been great to get individual temperature and precipitation time series for each basin, we instead used temperature and precipitation averages by ecoprovince, which is just a delineated area with similar climate. And so the outlines of the ecoprovinces are shown on the map that I have here, and there's typically around like 9 per state. So time series were just obtained from NOAA and Environment Canada for that. The fitting of DFA models was a multi-step process, and we followed methods that were just laid out in previous literature. So we first selected the number of trends in the model, and note that latent trends represent hypothetical time series or common trends that can't be explained by measured explanatory variables. Therefore, the intent of DFA is to create a model with a reasonable fit and a minimum M. So a higher M, or number of latent trends, will increase model fit, but it'll also cause more parameters to have to be estimated, which can complicate interpretation. So when selecting the number of trends, we therefore started with one trend, I guess. So all rivers are doing exactly the same thing, and required each additional trend to not only reduce AIC, but also explain a substantial proportion of the total variance. This was done to allow analysis of a relatively large data set and include only factors that explained a substantial portion of hydrologic variance. And so once the number of trends was selected, the next step was to select the error structure for the observation equation, or the R matrix. And so we tested 3 configurations, including different variances and no covariance, shared variance and no covariance, or shared variance and the same covariance between all rivers. And then we finally tested individual covariates for inclusion in model, our final best fit model, I guess. And covariates, so they were first added to the structure of our best fit model, where it had the number of trends and the error structure individually. And then after that, we used a forward stepwise procedure according to the AIC score from the previous step in order to get our final best fit model with covariates included. And so results from the DFA model fitting showed that between 3 and 4 latent trends were selected for each metric. For all metrics, the error structure, different variance, no covariance was selected. So in the table here, results from the single covariate models are shown. Results for each metric are shown going down the rows, and then the covariate delta AIC from the best fit model are shown in the row column combinations. So mean temperature and precipitation were consistently the best predictors. Temperature shows up in 3 of the metrics and precipitation shows up in all of them. And one caveat with this is that looking at all rivers simultaneously when you're assessing this And so although a given covariate may be important for a specific river, it might not be included in the final model if its utility isn't broadly applicable to all the rivers in our data set. And so next, we use that modified forward stepwise procedure to generate a best fit model, which could include multiple covariates. So all best fit models included mean precipitation, and for 3 of the metrics, it was actually the only covariate included. This suggests that the amount of precipitation has historically had the dominant influence on both extreme high and low flows compared with warming temperatures, which is consistent with, again, a study out of the Pacific Northwest. So one thing to note is that overall, our squared values were quite high given the relatively simple model structure, which is between 3 and 4 trends and 1 to 3 covariates. And so this just highlights that there's a ton of synchrony in river response to both measured and unmeasured variables. Okay, so moving on to more, I guess, in-depth DFA results, I'm only going to talk about peak flow magnitude and minimum flow magnitude, because I could not find a way to succinctly describe results from all 4 of the models. And these 2 are different enough that I think it's a useful comparison. So anyways, in our best fit model for peak flow magnitude, the only covariate included was mean annual precipitation. The graph here shows the coefficient for each river for mean annual precipitation, which is what that unlabeled x-axis is. And then the y-axis is just latitude. So since all time series and covariates are standardized before analysis, the loadings onto both latent trends and covariates can be thought of as effect sizes that describe the magnitude of the response of our flow metric to the given driver. And so the fact that mean precipitation was the only covariate selected and that basins with the largest loadings onto mean precipitation are actually rain basins in Southern California and more northern snow basins was a bit surprising. So we expect mean annual precipitation to have an impact on basins with snow, as in these basins, the largest flows of the year are typically either caused or augmented by snowmelt, and therefore related to the integrated climatic effects occurring through the entire snow accumulation season, rather than to individual winter storms. And so you'd expect these basins to have a higher loading onto mean precipitation. But we'd also expect storm-driven rain basins to load less strongly on mean precipitation, which integrates across the entire year. And so the reason for this, I'm pretty sure, is because precipitation in California, where those highest loadings for those rain basins are, tends to be far more seasonal in nature and comprised of fewer precipitation events. So in those areas, if you know the mean precipitation, you likely know something about the largest storm event of the year. And these plots that just popped up are just histograms that show the proportion of precipitation falling in each month for data from each of our eco-provinces. So you can see that the green facets, which are California eco-provinces, tend to have a higher proportion of total precipitation falling within just a few months. And so it's super intuitive in hindsight, but there was a good lesson for myself on comparing patterns across scales and the importance of understanding what an integrated metric like mean precipitation is telling you. And this is also likely the reason why maximum precipitation wasn't selected as a covariate in this model, because mean precipitation is informative for both low latitude rain basins and snow basins in general. It was a better fit across all of the data than just maximum precipitation. Okay, so on to shared trends for the DFA model. This graph here on the top shows each of the 3 latent trends estimated by the DFA model. And on the bottom is just a map of the spatial distributions of trend loadings, which again can be thought of as a coefficient on the trend. And so one thing that's readily apparent from these results is the clustering of these peak flow trends in particular geographic areas. So for example, Southern British Columbia and Washington for trend 1, Northern California and Oregon for trend 2. There's also a lack of coherent response associated with basin type. And so this suggests that the primary mechanism that determines flood risk across this area is the spatial distribution of winter storms. So that's not to say that river type doesn't matter or play some role in determining flood risks, but such effects are apparently secondary to storm track behavior affecting precipitation, which is relatively geographically located in a small area. But I guess this wasn't exactly what we thought we would see, given the large amounts of literature discussing reduced peak flows in snowmelt and some mixed basins due to winter warming, but really highlights the importance of interannual variation in addition to spatial variation. Okay, so moving on to minimum flow magnitude. And our best fit model for minimum flow magnitude, 3 covariates were included, including mean temperature and precipitation and a winter ENSO index. Again, the graphs show each river coefficient for each of the covariates on the x-axis, and I apologize, these are not labeled either, and the y-axis shows latitude. And so for these, the direction of the relationships are about what we would expect, where higher precipitation results in higher minimum flows and warmer temperatures result in lower minimum flows. And there aren't strong latitude or river type patterns in the loadings onto precipitation. However, the impact for temperature is much higher in mid-latitude basins. And for mixed and snow watersheds, this makes a lot of sense if we consider that winter temperatures in these areas are typically near freezing, and a warm winter can indicate reduced snowpack to sustain summer streamflow, thus lower minimum flow magnitudes. And for ENSO, overall loadings onto ENSO are much smaller than for either temperature or precipitation, indicating a reduced role in controlling these patterns through time. Yeah, just has less of an effect compared to temperature and precipitation. All right, so for the shared trends for minimum flow, mirroring what we saw with our monotonic analysis, minimum flow magnitude latent trends generally show clearly decreasing patterns through time. Although if loadings onto trends are negative, these patterns can be thought of as increasing, as you can see is the case for trend 3. So overall, the clustering of loadings onto minimum trends is much more dispersed than for peak flows, indicating processes that generate these minimum flows are operating on a much larger scale. Additionally, this is the exact same data as the stuff on the maps, except it's just displayed instead of on a map with latitude on the y-axis and the color of the points showing river type. And that's just because I think it's easier to illustrate the point that I want to make, which is that we do see an impact of river type when looking at trend loadings, particularly if you look at trend 1 and trend 3, where the interaction between latitude and river type actually is important in determining how river basins load onto these trends. However, again, it's hard to distinguish latitude versus river type for these. Okay, so I guess overall takeaways for this. First, climate covariates included in this analysis show that precipitation is a dominant control on the magnitude of duration of both high and low flow metrics compared to air temperature or global circulation metrics or river type when looking across rivers. And so when thinking about how this impacts future water management, precipitation projections are less certain than those for temperature. And this introduces additional uncertainty in terms of how Western rivers will respond to climate change. So also, I mentioned this before, but it's worth noting again that it was a bit of an all or nothing process when selecting covariates, and that a given covariate was either included for all rivers or for no rivers. So it's not to say that things like temperature don't have impacts, it's just that it didn't have a large enough impact across all basins to justify the inclusion in the model. And the second big takeaway is that there's really strong geographic synchrony in river trends, even after accounting for some of the effects of temperature and precipitation. There's sort of like 2 points I want to make with that. And the first is that this illustrates that most of the variability in these river metrics is dominated by year-to-year fluctuations that vary geographically rather than a specific trend through time or strictly by hydrology class. So undoubtedly, this is caused by my very generic climate covariates failing to capture important nuances of what's occurring on the landscape. So mean temperature and precipitation are useful, but only so much. And so while a big part of this seems obvious, I think it's important and useful reminder when thinking about how the future will look, that there will be a regional aspect to this that is stronger than something as simple as hydrology class, although that will certainly have an impact. So the second big takeaway is that potentially I should redo this analysis using spatial dynamic factor analysis to account for that unmeasured spatial autocorrelation in my data. Initially, I thought that by including spatially explicit covariates, I could account for this. Obviously, there's a lot of residual autocorrelation that needs to be accounted for, I guess, and that's what the DFA model is picking up. And so I know there's been at least one use of spatial dynamic factor analysis models for use in species distribution modeling, where the latent trends are not just trends through time, but trends through space and time, so latent spatial variables, I guess. And those latent trends have a term that represents spatial variation, represented by a Gaussian random field. So that's one sort of extension that I think would be super useful to do. And then one other small point is that, as it was probably clear, patterns are less coherent for high latitude rivers. And that's likely due to just having, I guess, a broader geographic distribution than some of my lower latitude rivers, in addition to some processes at work, like glaciers and permanent snow and ice. And so potentially future analyses would deal with that, perhaps by removing these sites from the analysis. And then that would allow, I guess, more explicit covariates to be generated as well. All right, and so with that, I guess I'd like to thank all of the collaborators on this. The project actually started when I took an applied time series analysis class lots of years ago, and then I kind of didn't do much on it for a while, but the skills in that were super useful. And then additionally, funding for this was through NSF GRFP. So I guess if anyone has any questions, I'm happy to take them at this time. Or just ideas for future extensions, or is there, ways to improve this analysis? Really, I'm open to anything.
Thanks, Lily. That was great. I can kick us off with a question that's not super fully formed and you should take with a grain of salt, because I would caveat it that I have no intuition for this system. But I sort of wonder, when you presented the results of your DFA, that all the models were showing the error structure being different variance, no covariance. And I wonder, do you think that's related to unmodeled spatial?
Yeah, I definitely think that. And that's one of the potential extensions, as opposed to a full-on spatial model, that I considered doing, was just to modify that R matrix in this, where the R matrix, instead of having no covariance across rivers, is something where, you can incorporate spatial autocorrelation. So the covariance is just directly related to how close rivers are in space. And so we think that would help. I actually tried doing that, and then I continually got convergence issues. I think it's non-trivial to fit them with so many time series in it. So yeah, that's something I'm actively working on doing. And you can, so either specifying the structure for that covariance, or just fitting an unconstrained model. And I imagine that naturally the spatial autocorrelation will pop out in that, where rivers that are closer together geographically are covary more strongly, I guess. So yeah, no, that's a really good point.
Cool, thank you. I see a raised hand, and a question, so I'll punt it to you.
Okay.
If you want to read it out loud. Do you see that?
Oh, did you evaluate whether there was a lag in the ENSO covariate on stream flow? No, I did not evaluate lags in any of the covariates. I considered doing it, and then just to keep the overall number of covariates down for this first pass analysis, I didn't. But yeah, that would make sense. I additionally thought of things like precipitation from the previous year, doing a 1-year lag on that as well, to maybe account for some groundwater effects. But no, that's a good point. And if there's any sort of papers or explicit reasons that would justify including the lag, I would love to hear about them as well.
Great. Peter says he will send you a
Great.
paper.
That's
And then
wonderful.
I'm going to unmute Elizabeth Holmes really quickly so
Okay.
that she can ask a question live. All right, you should be able to unmute yourself, Elizabeth.
Nice. Nice job, Lily. Great to see you putting to use those skills you learned in the time series course.
Slowly but surely.
So I had a question, if you had or if you thought about like trying to like zoom in on an area and kind of doing the DFA, but in a smaller area, so maybe you could see if there were not spatial features, sort of river features
Mhm.
that cause really more local correlation. Because I'm thinking now you're looking at a really high level, like the whole West Coast, and so
Mhm.
those really local differences probably don't pop out.
Yeah, no, that's a really good point. And I think that's also reflected in the relatively small number of trends over the large number of rivers. So I thought about doing that either, zooming in more locally for just like the Pacific Northwest, or just increasing the number of latent trends that are estimated to maybe pick up some more of that local scale variation. I like the idea of doing it just individually by region though, because I know the number of basins in a given area can skew DFA results to pick up more local variation where there's a lot of rivers, because you're explaining more variation in that larger number of rivers. So I think that'd be a good extension on it, and could maybe move beyond some of these like really broad, potentially clear patterns into some more nuanced results. Oh, and then I see more questions popping up. Oh, one is a comment. Oh,
Do you want
sorry.
me to read them?
I can just read the comment. So one is speaking to the point, you can imagine lakes and wetlands will have a large effect on snow. Yeah, definitely. Or large effect on flow. I think I said snow. Yeah, I would agree with that. And I think part of the screening for these climate reference rivers are that there's not man-made structures like reservoirs in them, but definitely, yeah, lakes and wetlands, I could see that impacting things like minimum flow strongly, even maximum flow too, actually. And then I see a question from Mark, which is, I wonder if you've considered differences in the variance of flows across latitudes, and specifically for your trend analysis, have you considered using biased random walks in lieu of the Mann-Kendall test, which would allow you to evaluate similarities or differences in the year-to-year variance? Yes, I definitely have, and I actually think I have code to run that. The reason I did the Mann-Kendall results, I guess, was just to have a basis of comparison with what a lot of other previous studies have done. So it really is like super duper duper widely used. And I kind of wanted to see, yeah, I guess I just wanted to compare DFA results to this more commonly used method as a first pass in order to see sort of what the different methods tell you, potentially positioning DFA as like an alternative to using this Mann-Kendall. But I do agree that biased random walks are a good next step with this analysis. I hope that answered it, the question. And then there's a question from, okay, Mark says, okay, thanks. There's a question from Amy, which is, would you expect different patterns in other regions? What might differ in flatter terrain or with less directed storm paths? Yeah, I guess flatter terrain, I would expect other factors aside from individual storm events. Or maybe I guess I would expect more synchrony in rivers, and then differences would be controlled by factors other than these like, very small storm path events that we see on the West Coast. Yeah, I guess if that answers it. Oh, please, okay. Please send me your email. Okay, and I think that is all the questions.
Yep, I think that's right. I'm not seeing more questions coming in, but let me check for some raised hands. I'm not seeing any. So I think with that, we should give Lily a virtual round of applause and say thank you so much for coming. Again, this was our last quantitative seminar of the quarter. So thanks everybody for coming to all the talks this quarter. Enjoy the break. We'll be releasing our schedule for the winter quarter in a few weeks here. We've got an exciting lineup for you, so we'll see you in the new year.